Let me ask you something that I think you've probably wondered about yourself. When you were 12 years old, you could sprint around a field for hours, scrape your knees, dust yourself off, and keep right on going. But now, maybe you're 40, 50, 60, you sit too long in one spot and you're wiped out. A single flight of stairs has you catching your breath at the top. So what on earth happened? Now, I know what you're thinking. You're thinking, oh, that's just aging. And look, I understand why you'd say that. But here's the thing. That's not actually an explanation. That's a name you've put on a mystery and then stopped asking questions. A physicist doesn't do that. A physicist looks at a phenomenon like that and asks, what is the actual mechanism? What's happening at the level of atoms and molecules inside your body that produces this feeling? And when you dig into it, really dig in, the answer is genuinely strange. It's not that you're simply running low on fuel. It's not some battery wearing out. The real explanation reaches all the way down to the most fundamental laws of the physical universe, the same laws that govern how stars burn and why engines work, and how the cosmos itself evolves. So let's figure this out together. By the time we're done, you're going to have a real understanding of what energy means inside a living body, why a principle called the second law of thermodynamics has a deeply personal stake in your existence, and why, from a physics standpoint, the way we age isn't some biological accident. It's embedded in the structure of reality itself. But before anything else, let me be precise about what I mean when I say energy, because the word gets thrown around in ways that make physicists wince. Energy, in physics, means the capacity to do work. That's it. It's a measurable quantity, counted in joules or calories, and it obeys strict mathematical rules. It is not some mystical life force. It's not chi or prana, or any of those things people sometimes invoke. When you feel full of energy, something real and measurable is happening in your cells. And when you feel exhausted, something real has changed in the chemistry of your body. Reaction rates have shifted. Concentrations have changed. This is not poetry. It's science. And the beautiful thing about that is, once you understand the mechanism, you actually have some power to influence it. Not total power. Some things are genuinely out of your hands. But understanding the machinery is always the first step toward affecting it. So let's start somewhere everyone can relate to. Breakfast. Suppose you had some eggs this morning, maybe toast, maybe coffee. What actually happens to that food? Most people would say it gives them energy, and that's true enough, but it's terribly vague. Let's get specific. The carbohydrates in that toast get dismantled into glucose molecules, simple sugars. Those molecules make their way into your cells. And here's where things get interesting, because inside your cells are these tiny structures called mitochondria. They're about the size of bacteria, which is not a coincidence. We're fairly confident they were bacteria, billions of years ago, that got absorbed by larger cells and ended up forming a partnership that's persisted ever since. A very ancient collaboration. These mitochondria are your cellular power plants. They take in glucose and run it through a cascade of chemical reactions that extract energy from it. But here's what's clever. They don't release that energy all at once in some uncontrolled burst, the way wood burns in a fire. Instead, they do something much more elegant. They capture the energy and package it into a specialized molecule called ATP, adenosine triphosphate. Now, ATP is a marvelous little device. It has 3 phosphate groups hanging off it, and the bonds holding those phosphates together are what we call high-energy bonds. Think of it like a compressed spring. The energy is stored in that tension, waiting to be unleashed the moment it's needed. And here's a number that ought to stagger you. Your body, right now as you sit there, is making and consuming roughly 50 kilograms of ATP every single day. 50 kilograms. That's probably close to your own body weight, or possibly more. How can that be? Well, because each individual ATP molecule gets recycled over and over again. It's like a rechargeable battery that gets plugged back in thousands of times a day. To really feel the scale of this, consider, at any given moment, your body holds only about 50 grams of ATP total. 50 grams. Yet you cycle through 50 kilograms in a day. That means each molecule is being reused roughly 1,000 times, once or twice every single minute, all day long, without stopping. And a single cell, just one out of the trillions you have, burns through about 10 million ATP molecules every second. 10 million per second. per cell. The numbers are almost impossible to hold in your mind, and yet this entire operation is running right now without you paying it the slightest bit of conscious attention. Everything you do runs on this currency. Your heartbeat, ATP. Your thoughts, ATP. The simple act of sitting still ATP, because your cells are constantly maintaining themselves, pumping ions, building proteins, keeping everything organized. Your brain alone consumes about 20% of your body's total energy output. A fifth of everything you eat powers that 3-pound structure in your skull, which is doing constant work, firing neurons, sustaining electrical gradients, assembling neurotransmitters. And it never fully stops, not even when you're asleep. Certain brain processes actually intensify during sleep, so when you say you feel tired, what you're really saying is that somewhere along this chain, from food to mitochondria to ATP to action, something isn't performing the way it once did. Now let's talk about what goes wrong as we get older, because this is where the story becomes genuinely interesting. Your mitochondria are not perfect machines. When they convert glucose into ATP, they inevitably produce other things as well. Byproducts, specifically things called reactive oxygen species, free radicals. You've probably heard of them. Think about a car engine. It burns fuel and generates motion, but it also generates exhaust, heat, pollutants, waste. Your mitochondria do the same. They're not 100% efficient, and this is not a flaw in their design. It is a fundamental consequence of the laws of thermodynamics, and there is no escape from it. Let me be a bit more precise here. In thermodynamics, we think carefully about what it means for an engine to be efficient. A theoretical ideal, called a Carnot engine, would convert energy with no losses at all. But a Carnot engine would have to operate infinitely slowly, which means in practice it's unreachable. Real machines, biological or otherwise, always fall short of that ideal. Your mitochondria are actually quite impressive, about 40% efficient at capturing energy from food. For comparison, a typical car engine is around 25% efficient, so your cells are beating the automobile industry. But that still means 60% of the energy from your food leaves your body as heat. That's why you're warm. You are continuously radiating waste heat from your own metabolism. And along with that heat, you're releasing those chemically reactive free radicals. Here's the problem. They're aggressive. They ricochet around inside your cells, and they damage things. They damage proteins. They damage cell membranes. And most critically, they damage DNA, including the DNA that lives inside the mitochondria themselves. Here's something remarkable that most people don't know. Your mitochondria have their own DNA. It's entirely separate from the DNA in your cell nucleus. This is a leftover from their bacterial days. They carried their own genetic material when they arrived billions of years ago, and they've held on to it ever since. And this mitochondrial DNA is far more vulnerable to damage than nuclear DNA, for several reasons stacking on each other. First, it's physically close to where the free radicals are generated, like living in the apartment directly above a factory floor. Second, it lacks the protective proteins called histones that wrap around and shield nuclear DNA. It's more exposed. Third, the repair systems for mitochondrial DNA are simply less sophisticated than those for nuclear DNA. So here's the situation you're in. Your power plants produce the energy that keeps you alive, but in doing so, they gradually damage themselves, like an engine that corrodes from its own exhaust. And across decades, this damage piles up. The mitochondria become less effective. They produce less ATP. And because damaged mitochondria are also leakier and less controlled, they produce even more free radicals, which causes more damage, which produces more free radicals. It's a vicious cycle running in one direction. And you experience it. You feel it as persistent fatigue, as slow recovery from exertion, as needing more sleep, as that sense that your drive and stamina have quietly slipped away somewhere. But I want to pull back now and show you the physics underneath all of this biology, because there's something deep here. There was a physicist named Erwin Schrödinger, famous, yes, for a thought experiment involving a cat, who wrote a small book in the early 1940s called What is Life? It was a remarkable thing, because it asked the simplest possible question. What actually distinguishes living things from non-living things? What's the special ingredient? Schrödinger was a quantum physicist. He invented the wave equation that describes how particles behave in quantum mechanics. So he knew fundamental physics at a serious level. And when he turned that lens on biology, he noticed something that looked almost paradoxical. Living things maintain order. They stay organized. but the universe in general tends toward disorder. How does life pull this off? His answer was elegant. He said living organisms sustain themselves by consuming what he called negative entropy, by feeding on order from their environment. Now that sounds strange, so let me explain what entropy actually is. Entropy is a concept from thermodynamics, developed by a German physicist named Rudolf Clausius in the 1860s. People often describe it as disorder, but that's a bit loose. More precisely, entropy measures how spread out and dispersed the energy in a system has become. Low entropy means energy is concentrated, organized, available to do useful work. High entropy means energy is diluted, scattered, degraded into the kind of heat that can't really drive anything. Let me give you a concrete picture. Suppose you have a hot cup of coffee sitting in a cold room. The coffee has relatively low entropy. The heat is concentrated in one place. Leave it alone for an hour and it cools down. The heat flows outward into the air. Eventually, the coffee and the room reach the same temperature. The energy is now evenly spread. Entropy has gone up. And crucially, this never runs backwards on its own. You will never see a cup of coffee spontaneously get hotter while the room around it gets colder. That would require a decrease in entropy, and it simply doesn't happen. This is the second law of thermodynamics. In any isolated system, entropy tends to increase. Things fall apart, hot things cool down, organized structures crumble. This is also, and this is one of my favorite facts in all of physics, the only law that gives time a direction. Newton's laws, Maxwell's equations for electromagnetism, even the equations of quantum mechanics, run them backwards in time, and they still work perfectly well. But the second law only works in one direction. The past has lower entropy than the future. That asymmetry is the arrow of time. It's why we remember yesterday but not tomorrow. It's why causes come before effects. Entropy is what makes time flow the way it does. So how does life resist this? How does your body, with all its intricate molecular machinery, stay organized? Schrödinger's key insight was that living things are not isolated systems. They're open systems. They import low-entropy energy from outside, in the form of food and sunlight, and they export high-entropy waste back out in the form of heat and metabolic byproducts. They maintain local order by producing disorder elsewhere. The total entropy of the universe still increases. The second law is satisfied. But inside the organism, the low-entropy state is temporarily sustained. When you eat that piece of toast, you're not just taking in calories. You're taking in organized energy. The chemical bonds in those carbohydrate molecules represent structure and order. Your body breaks down that structure, captures some of the released energy in ATP, and expels the rest as heat and waste. Order flows in, disorder flows out. Life, in this sense, is an upstream swimmer. It's constantly fighting the current flowing toward chaos. Now here's what changes with age. That upstream swimming becomes less efficient. Think about the energy conversion happening in your mitochondria. Every conversion loses something. Some energy degrades into heat rather than getting captured as useful ATP. The second law guarantees this. In a young, healthy cell, the machinery runs cleanly. The losses are relatively small. Damage gets repaired quickly. But as time accumulates damage in the mitochondria, they become leakier. More energy escapes as heat instead of being captured. The repair systems themselves get worn down and stop catching errors as reliably. The result is that you're consuming just as much food, maybe more, but getting less usable energy out of it. You're running a power plant with progressively more worn-out turbines. Let me give you another way to picture this. Imagine a bucket of water at the top of a tall waterfall. That height represents potential. The water can fall and turn a wheel and do real work. Your food is like that elevated water. It has potential. Your mitochondria are like the wheel, capturing that potential as it falls. Now in thermodynamics, we have a specific term for the portion of energy that can actually be extracted to do work. We call it free energy. Not all the energy stored in your food is free energy. Some is bound up in forms you can't extract. This distinction is subtle but important. The first law of thermodynamics tells you that energy is conserved. It can't be created or destroyed. But the second law tells you that the quality of energy declines. Chemical energy in food is high quality, organized, concentrated, available. Dispersed heat in the room is low quality, spread out, hard to harness. Every time you convert energy from one form to another, some quality is lost. When you burn a log, the total energy doesn't disappear, but the concentrated chemical energy in the wood becomes diffuse heat in the air. Same total, lower quality. High quality energy has low entropy. Low quality energy has high entropy. And as your mitochondria accumulate damage with age, their ability to capture high-quality free energy before it degrades into heat diminishes. The wheel gets rusty. The water still falls, but less of it gets converted into useful rotation. Let me put some real numbers to this. A gram of glucose carries about 4 kilocalories of energy. A perfectly efficient system could capture all of that as ATP, but your mitochondria actually capture around 40%. The rest becomes heat. That 40% is actually impressive. Car engines typically manage only about 25%, and many power plants hover around 30 to 40%. Your cells are doing quite well, but if age and damage drop that efficiency from 40% to 35, then to 30, it adds up significantly over the course of a day's worth of ATP turnover. And there's another problem beyond raw efficiency. Damaged mitochondria are slow to respond when demand suddenly increases. When you're young and you start exercising, your mitochondria ramp up ATP production rapidly. The proteins in the electron transport chain are intact. The membranes hold together. Everything accelerates smoothly. When you're older, that response is sluggish. Instead of producing more ATP cleanly, stressed mitochondria are more likely to leak, producing reactive oxygen species instead of useful energy. This is why you might feel reasonably okay at rest, but genuinely struggle the moment you push yourself. Your baseline is maintained, but your peak capacity has eroded. And here's a consequence that surprises people. Even if you eat the same amount you ate at 25, you might gain weight at 50. Not because you're being undisciplined, but because your body extracts usable energy from that food less efficiently, and more of it ends up stored as fat or dissipated as unproductive heat. Now here's something that researchers have actually measured, and the results are more surprising than you'd expect. In the first year of life, a baby's metabolic rate, adjusted for body size, is about 50% higher than an adult's. Babies are tiny furnaces. They're growing, assembling tissue, building a brain. And building a brain is extraordinarily expensive. In an infant, roughly 60% of total energy goes to the brain alone. 60%. That's why babies sleep so much. The brain is running a massive construction project during sleep, wiring itself, pruning connections, laying down the architecture of a mind. Think of it as a round-the-clock renovation. Then through childhood and adolescence, the metabolic rate per unit body size gradually comes down. By around age 20, it levels off. And then, here's the part that surprises people, it stays essentially flat from your 20s all the way to about 60 years old. Yes, flat. The widespread belief that your metabolism mysteriously crashes in your 30s or 40s is largely a myth. A large study published a few years ago tracked over 6,000 people from 29 different countries, ranging in age from 8 days old to 95 years, and used a technique called doubly labeled water to precisely measure caloric expenditure. The finding was clear. Adjusted for body size and composition, metabolic rate doesn't decline significantly between the ages of 20 and 60. Now, unadjusted total metabolic rate does tend to fall during those decades, but that's because people typically lose muscle mass and gain fat. Muscle is metabolically demanding tissue. It burns energy just to exist. Fat is cheap to maintain. As your body composition shifts, your total energy needs fall, but that's a consequence of what your body is made of, not a decline in cellular efficiency. If you preserve your muscle mass, you can sustain your metabolic rate well into middle age, which is exactly why resistance training matters so much. After 60, though, something genuine changes. From 60 onward, there is a real decline, about 0.7% per year. By 90, your metabolic rate is roughly 25 to 30% lower than it was in middle age, even after you account for changes in body composition and activity level. This is the accumulated damage I described. the slow degradation of mitochondrial function, the buildup of errors, the gradual decline that the second law was always predicting. And I want to pause here because I said the second law predicts this, and I want to make sure you feel the weight of that statement. The second law of thermodynamics is not a tendency or a guideline. In any real system doing real work and converting energy, entropy must increase, damage must accumulate, efficiency must decline. There's no workaround. Some physicists have calculated a quantity they call lifespan entropy, the total amount of entropy your body produces across an entire lifetime. And remarkably, this number comes out roughly consistent across different individuals, on the order of 11,000 kilojoules per Kelvin per kilogram of body mass. What does that number mean? It's a measure of how much thermodynamic irreversibility your body has processed, how much order you've converted to disorder, how much free energy you've degraded into heat. Think of it as a kind of budget. You start with the capacity to process a certain amount of entropy while maintaining your organized state. Different species have different budgets, scaled roughly with body mass. But within a species, the figure is surprisingly consistent, as if there's a fundamental thermodynamic limit to how much processing a given amount of biological tissue can sustain before it breaks down irreversibly. That's a strange way to measure a life, in units of entropy, but it tells you something true and deep. It points toward what's called the rate of living theory, the idea that metabolic rate and lifespan are inversely connected. Burn fast, die young. Burn slow, live long. It's not the whole story, but it captures something real. Consider this. A hummingbird and an elephant process roughly the same amount of entropy per kilogram of body mass over their respective lifetimes. The hummingbird gets through its entire thermodynamic budget in just a few years, its wings beating 80 times per second. The elephant moves through the same journey over 60-odd years at a much more measured pace. Same thermodynamic journey, very different speeds. But I don't want you to take from this a feeling of fatalism, because the second law doesn't dictate how fast entropy has to increase. It just insists that it must increase. And that gap between must increase and must increase this fast is where you have real agency. There are things that accelerate entropy production in your body. Overeating is one. When you flood your mitochondria with more energy than they need, they produce more waste and more damage. Inactivity is another, and here's the counterintuitive part. Not using your mitochondria makes them weaker. They degrade from disuse, and there are things that slow the accumulation down. Moderate caloric restriction, eating a bit less than maximum appetite, has extended lifespan and preserved mitochondrial function in many organisms studied in the lab. Exercise, even though it temporarily increases energy consumption, makes your mitochondria stronger and more numerous in the long run. Stressing a system appropriately tends to make it more robust. Sleep matters enormously. During sleep, your body carries out a large proportion of its cellular repair work. Skimp on sleep and the damage piles up faster than it can be addressed. Think of it as scheduled maintenance that you can't afford to skip. Here's a thought experiment. Imagine two genetically identical twins at birth. Same genes, same mitochondria, same everything. One of them lives actively, exercises consistently, eats in moderation, sleeps well. The other is sedentary, overeats, sleeps poorly. By 60, they will have diverged dramatically. The active twins' mitochondria will still be converting food to ATP with reasonable efficiency, generating relatively few damaging byproducts. The sedentary twins' mitochondria will be struggling, leaky, inefficient, generating more damage. The second law applies to both with equal impartiality, but the rate at which they're being carried toward thermodynamic equilibrium is quite different. The active twin has found more efficient ways to swim upstream. Now let me address a misconception that I think trips a lot of people up. When you feel exhausted, you might instinctively reach for more fuel, more food, more coffee, more sugar. But usually the problem isn't a shortage of fuel. The problem is the inability to convert fuel into useful work efficiently. Think about someone carrying significant excess body fat. They have enormous energy reserves stored, yet often feel chronically tired. Why? Because the machinery that processes fuel is under strain. Their mitochondria are stressed. It's not that there's no wood for the fire, it's that the fireplace is choked with soot and can barely burn what's already there. You don't need more fuel, you need to clean the fireplace. This is exactly why exercise can reduce fatigue, even though exercise uses energy, a thing that seems paradoxical until you understand the mechanism. In the short term, yes, exercise tires you out, but over weeks and months of regular exercise, your baseline energy level rises. Why? Because when you push your mitochondria hard, when you demand ATP at rates they're not used to, this stress, provided it isn't excessive, triggers a response in your cells. They detect the increased demand and they respond by building more mitochondria. This is called mitochondrial biogenesis, but they also do something just as important. They get rid of the mitochondria that are too damaged to pull their weight. Under genuine demand, you can't afford to carry broken equipment. This brings me to a process called mitophagy. Your cells have a quality control mechanism by which they identify damaged mitochondria, tag them for destruction, and break them down to recycle their components. The name comes from the Greek for mitochondrion and eating. Your cell is literally consuming its own defective power plants. It sounds severe, but it's a crucial maintenance system. In young cells, this works well. Damaged mitochondria are identified and removed, replaced by fresh functional ones. But as we age, mitophagy becomes less effective. Damaged mitochondria linger, they accumulate, they sit there leaking free radicals and producing inadequate ATP, cluttering the cell and making things worse. One of the key biological differences between a young cell and an old one is that a young cell takes out its garbage reliably, and an old cell lets it pile up. Exercise stimulates mitophagy. It essentially signals to your cells, we need the good equipment working, clear out the rest. Fasting, intermittent fasting specifically, also stimulates mitophagy. When food is scarce, your cells shift into a recycling mode, becoming extremely efficient at salvaging and reusing their own components. There's a molecule called AMPK that functions like a fuel gauge for your cells. When cellular energy runs low, AMPK activates a cascade of responses including cleanup and repair processes, mitophagy among them. Exercise activates AMPK. Fasting activates AMPK. Caloric restriction activates AMPK. This might be part of the explanation for why moderate stress, not severe destructive stress, but mild challenge, what researchers call hormesis, seems to be beneficial for longevity. A manageable stress triggers adaptive responses that leave cells stronger and more resilient than before. Now, here's something I find genuinely beautiful about this from a physics standpoint. Your body isn't simply a machine that consumes fuel to produce output. It's a self-maintaining, self-renewing system. In fact, most of the atoms currently in your body weren't there 7 years ago. Your proteins get broken down and rebuilt. Your cell membranes are constantly replaced. Even the minerals in your bones turn over. The atoms cycle through. So why do you age at all? If you're perpetually rebuilding yourself, why don't you just rebuild perfectly and stay perpetually young? The answer comes back to the second law. Those very rebuilding processes require energy, and they involve copying information, reading molecular blueprints, and following instructions. And every time you copy information, every time you do work, there are chances for error and sources of waste. Imagine maintaining a building by constantly replacing every brick. If your brick-making factory itself is slightly degraded, the replacement bricks will be slightly inferior to the originals. And gradually, imperceptibly, the building deteriorates. Not because you stopped maintaining it, but because the maintenance process itself is imperfect. Your DNA is the instruction manual for building your cells. It's written in a 4-letter code. The base is A, T, G, and C, and it specifies every protein your body can make. When a cell divides, it has to duplicate that entire code. The enzymes that perform this duplication are extraordinarily accurate. Roughly 1 error per billion bases copied. That's comparable to transcribing the entire Encyclopedia Britannica 1,000 times and making only a single typographical error. But 1 in a billion is not 0. You have trillions of cells dividing throughout your life. Errors accumulate. Mutations. Most are harmless, some get caught and repaired, but a few slip through. And beyond replication errors, there's constant external assault, radiation, environmental chemicals, and those free radicals we keep coming back to. Your DNA is damaged and repaired continuously. Usually the repair wins, but sometimes the damage is repaired incorrectly. Sometimes it isn't repaired at all. Over decades, the blueprint becomes less legible. The proteins built from it are slightly less precise. They don't fold quite right. They don't function quite as well. And here's the cruel irony. The repair machinery is itself made of proteins, which are built from the increasingly degraded blueprints. So the repair systems gradually lose their own fidelity. The worse the blueprint, the worse the repair. The worse the repair, the worse the blueprint. Information degrades. That's entropy operating at the level of data, not just heat. And as the information degrades, the structures that information encodes become less precise and less functional. This connects to something deep in theoretical physics. A physicist named Rolf Landauer demonstrated in the 1960s that erasing information has a thermodynamic cost. It produces heat. Information is physical. It has thermodynamic consequences. Your cells are constantly processing information, reading DNA, assembling proteins, sending and receiving molecular signals. Every time information is processed, there's a possibility of error. Every time it's copied, there's potential for degradation. This isn't a biological quirk. It follows from the same foundational principles that govern computer memory and communication theory. It is inescapable. This is the deep irony at the heart of living systems. The very process that sustains you, metabolism, energy conversion, is simultaneously the process that slowly undoes you. It's like a candle. The flame is brilliant. It gives off light and warmth, but it's consuming the wax as it burns. Let me step back for a moment and think about what all of this means at a larger scale, because I think it's actually quite profound, and maybe even a little liberating. The laws of thermodynamics are universal. They apply to stars, to galaxies, to car engines, to your body. Nothing gets an exemption. For a long time, people believed there might be something special about life, some vital force, some ingredient that physics couldn't account for, that made living things fundamentally different from inanimate matter. We know now that's not true. Your body is assembled from carbon, hydrogen, oxygen, nitrogen, and a handful of other elements. The same atoms that make up rocks, ocean water, and the air you breathe. There's no special life atom, no secret ingredient. What makes you remarkable is the arrangement. The staggering complexity and precision of how those atoms are organized, and the fact that this organization sustains itself temporarily against the relentless current of entropy. But it does so by working within physics, not in spite of it. It uses the laws rather than violating them. Think of a refrigerator or an air conditioner. It makes the inside cold. Does it violate the second law? No. It pumps heat to the outside. The total entropy of the system, room plus refrigerator, still increases. But inside the refrigerator, order is locally maintained by exporting disorder elsewhere. Life does exactly this with order and energy. You are not a ghost operating a biological machine. You are a process, a staggeringly complex, beautifully organized process of energy transformation, running according to the same rules as everything else in the universe. The atoms currently constituting your body have existed for billions of years. The hydrogen atoms were produced in the first few minutes after the Big Bang. The heavier atoms were forged in the cores of massive stars that burned out and exploded long before our solar system existed. You are assembled from stardust, and those atoms have been part of many things before they ended up as you, part of ancient trees, prehistoric oceans, other organisms, other people. Atoms cycle endlessly through the biosphere. Right now, you are a temporary configuration of very old matter, a configuration that takes in energy, does extraordinary things, and will eventually release those atoms back into the world, where they'll become part of other configurations. Other organisms, other patterns. When you feel fatigued, that is not your willpower failing you. That is physics, measurable, real changes in the molecular machinery of your cells. There's nothing to be ashamed of in it. It's as natural as water flowing to a lower elevation. And when you exercise, when you sleep enough, when you eat thoughtfully, you are not fighting physics. You're working with it. You're optimizing the thermodynamic processes running inside you. You're keeping your power plants in better shape. You're slowing the accumulation of damage. You cannot reverse the second law. You cannot live indefinitely, but you can influence the rate. You can, within real limits, choose how quickly you move toward equilibrium. Let me tell you one more thing before we close. Temperature and the rate of chemical reactions are deeply connected. Without needing the exact mathematics, here's a useful rule that chemists rely on. For roughly every 10 degrees Celsius rise in temperature, the rate of chemical reactions approximately doubles. This is called the Q10 rule. It's approximate, but it gives you the right intuition. Your body is warm, about 37 degrees Celsius, and that warmth accelerates all your metabolic reactions, letting you move quickly, think quickly, respond quickly, things that cold-blooded animals cannot do at low ambient temperatures. A lizard on a cool morning is essentially paralyzed. It has to absorb heat from its environment before its chemistry can run fast enough to function. You, on the other hand, generate your own heat as a byproduct of metabolism and maintain a constant internal temperature no matter what the weather is doing. This is what it means to be warm-blooded or endothermic, but there's a cost built into this arrangement. Faster reactions mean faster damage accumulation, faster entropy production. It's a fundamental trade-off, living fast versus living long. Researchers have noticed that animals with lower body temperatures tend to live longer on average. A tortoise runs cool and slow and can live well over 100 years. A hummingbird is an intensely hot little creature and lives just a few years. Now, you might object, but hummingbirds are tiny. Maybe size explains the lifespan difference. And size does matter. Smaller animals generally have faster metabolisms and shorter lives. But even after correcting for body size, there's still a relationship between metabolic rate and longevity. Animals that burn fast tend to die younger. Warm-blooded creatures like us have made a particular bargain. We burn brightly, which gives us speed, flexibility, and the ability to be active in cold environments. But we burn out relatively quickly compared to some other lineages. That's the trade we've made. There's a concept called the rate of living theory, which proposes that each organism has a fixed total amount of metabolic energy to spend over its lifetime. Once it's spent, it's done. Different species spend it at different rates. This theory in its original form is too simple. Birds, for instance, have very high metabolic rates, yet often live much longer than similarly sized mammals, which suggests that other factors like antioxidant defenses and mitochondrial efficiency play important roles. But the core observation, that metabolic rate and longevity are connected, seems to be real. Interestingly, small reductions in body temperature have been associated with extended lifespan in laboratory animals. Running the engine slightly cooler appears to reduce wear. I'm not recommending you go live in a walk-in freezer, but it's worth noting that during sleep your body temperature drops by about 0.5 degrees Celsius. This might be one of the reasons sleep is so restorative. The engine cools slightly, reactions slow, and the repair systems get a better window to catch up with the accumulated damage. So, what's the answer to the question we started with? What actually happens to your energy as you age? The real answer is that your energy processing machinery degrades gradually. Your mitochondria accumulate damage. They become less efficient at capturing the free energy in your food as ATP. More energy escapes as heat. More damaging byproducts are generated. The repair systems lose their edge. The vicious cycle tightens. When you were young, your mitochondria were like a fleet of new vehicles, running cleanly and efficiently, converting fuel to motion with minimal loss. With age, they become more like older vehicles with worn engines. They still run, but they use more fuel to cover the same distance. They produce more exhaust. They're slower to respond when you push them. You need more sleep to feel restored. You recover more slowly from exertion. You fade earlier in the evening. You have less resilience against physical demands. Your temperature regulation may become less precise. You feel cold more easily or have trouble cooling down when you're hot. These aren't signs of weakness of character. They're physics, real, measurable changes in real cells. There's nothing wrong with you as a person. This is the universal experience of being an energy-transforming system in a universe governed by the second law. But it is not destiny in the sense of being entirely fixed. Your choices genuinely matter. Exercise, especially resistance training, maintains muscle mass, stimulates mitochondrial biogenesis, and activates mitophagy. Sleep, 7 to 9 hours for most adults, is when the bulk of cellular repair occurs. Eating a moderate amount, not too much, not too little, reduces unnecessary strain on your mitochondria. Eating actual whole food, vegetables, grains, protein, rather than highly processed products, reduces the inflammation that accelerates cellular damage. Managing chronic stress matters because sustained high cortisol accelerates wear on your cells. Social connection matters. Isolation appears to have measurably toxic effects at the cellular level, and keeping your mind engaged seems to protect the mitochondria in brain cells specifically. None of this will make you immortal. The second law doesn't negotiate, but it can shift the curve, giving you more years of genuine vitality, more years of feeling like yourself, more years of capacity. The second law will ultimately win. It always does. But you get to decide how you play the game while it's running. And maybe there's something quietly comforting in all of this, because it means you are not separate from the universe. You are part of it. You are a pattern in the flow of energy, a beautiful, temporary, self-aware pattern, like a wave moving across the surface of water, or a vortex persisting in a stream. The pattern maintains itself for a while, does extraordinary things, and eventually dissolves back into the background. Schrödinger asked, "What is life?" And his answer, feeding on negative entropy, drawing order from the environment, is a physicist's answer. It says life is a thermodynamic process, a very special one, yes, a very complex one, certainly, but still a process obeying the same rules as everything else. The atoms in you were forged in stellar cores billions of years ago. The energy flowing through you is the same energy that moves through the rest of the cosmos. The laws governing your mitochondria are the same laws governing black holes, nuclear reactors, and the slow cooling of the early universe. You are not an exception to physics. You are physics, doing something genuinely remarkable for a while. When your power plants begin to falter, when your repair systems lose their sharpness, when entropy finally gains the upper hand, that isn't a tragedy in any physical sense. Personally, yes, it feels like one, but physically, it's simply the universe following its own rules, water finding its level, heat dispersing into the cold. You are a flame, burning brightly for a time. Eventually the fuel diminishes, the flame dims and goes out. That's not sad, that's just physics, and physics, whatever else you might say about it, is scrupulously honest. But here is the extraordinary thing about being a flame that understands its own nature. You can appreciate the burning. You can stand back and marvel at the process. You can actually comprehend what is happening to you and why, at the level of atoms and entropy and free energy and the arrow of time. No other flame in the known universe, as far as we can tell, understands itself the way you do. So here's the question I'd like to leave you with, and I genuinely want you to think about it. Now that you know what you know about entropy and free energy and the thermodynamic life of your mitochondria, has it changed anything? Does seeing the mechanism clearly alter how you experience being alive? Write something down. I'd genuinely like to know what you think.